Okay. Uh, uh, so thanks for coming. So this is a session of Blink Allocator. So I am Haraken, and this is a member of the memory team. So we have 5 members from Tokyo and Singapore at Opera. So what's the goal of the Blink Allocator? So our goal is to develop the best memory allocator in Blink that is fast, secure, and space efficient. So more specifically, fast means 60 FPS GC, small allocation overhead, and good memory locality. And secure means no use after freeze. And space efficient means no memory leaks, no out of memory, and small footprint. So this is our goal. So before taking a look at the details, let's understand the current status around the Blink allocators. So currently, in the V8 side, we have a V8 garbage collection. And in the Blink side, we have Oilpan, PartionAlloc, TCMalloc, and system allocator. And as you can see, it's crazy to mix 4 allocators in Blink. So conceptually, 2 allocators would be enough. So one allocator for GC'd objects, and the other allocator for non-garbage collected objects. So our goal of the Blink allocator is like this. So in the Blink side, we want to unify all allocators into Oilpan and more optimized PartionAlloc. So meaning that we want to remove TCMalloc and system allocator from Blink. And also, we want to implement a better coordination between V8 garbage collection and Oilpan and PartionAlloc. So this is a big picture of the Blink allocator. So specifically, we have these action items. So the first one is shipping Oilpan. So this is the first priority. And the second one is optimize PartionAlloc based on the experience we learned in Oilpan. And the third one is PartionAlloc everywhere, which means we want to replace TCMalloc and system allocator in Blink with PartionAlloc. And everywhere may mean everywhere in Chromium, but we are not sure. So we want to replace allocators in Blink with PartionAlloc at least. And the fourth one is we want to implement a good memory coordinator to coordinate memory, coordinate allocators in the renderer processes. So, okay, so let's take a look at these action items one by one in details. So the first one is shipping Oilpan. So this is the current status. So most modules objects are already working with Oilpan by default. And on the other hand, many core objects are working with Oilpan only on Oilpan views. So this contains node, CSS value, SVG, frame, window, WebGL, event target, and a bunch. So our first priority is to enable Oilpan for these objects by default as soon as possible. So the shipping criteria we have agreed on the last BlinkOn was to achieve no significant performance or memory regression in any metric, in any telemetry benchmark, in any platform. So in particular, the key metrics was execution time, pause time, and peak memory usage. Unfortunately, we met the criteria last month and published a final performance report and approved to ship it for core objects. So this is the performance data for execution time, pause time, and peak memory usage. So the first one is execution time. So in this graph, the x-axis is a list of benchmarks, so micro benchmarks in Blink. So there are a lot of benchmarks. And the y-axis is performance improvement or performance regression of Oilpan. So for example, this blue bar indicates that for this benchmark, Oilpan runs 20% faster than non-Oilpan. So as you can see, okay, so and the red line indicates the performance result 6 months ago. And the blue bars indicate the performance result of the latest Oilpan. So as you can see, we have accomplished a significant performance improvement in the past 6 months. And the average line is here. So overall, Oilpan runs much faster than non-Oilpan. So overall, Oilpan runs faster than non-Oilpan on all platforms. And Oilpan is going to make one of the most significant performance improvements this year. And the second metric is pause time. So regarding pause time, Oilpan implements lazy sweeping. which means that the marking phase is conducted in one go, but the sweeping phase is split into chunks. So the pause time becomes the marking time. The complexity is order live of live objects. And also, Oilpan is already integrated into the Blink scheduler. So these marking tasks and sweeping tasks are scheduled in idle tasks by the Blink scheduler. And according to our measurements, we observed no regression in the frame times metric in any smoothness benchmark on Nexus 4 and Nexus 7. This implies that Oilpan won't regress FPS. And also, we confirmed that almost all GC tasks in real-world websites are scheduled in idle tasks. So this is a very good news. And the third metric is peak memory usage. So as of January, there was no regression. So however, as of now, there are 5% regressions in newly added benchmarks called memory.top7 stress. And I think this is a bug. So we are now actively investigating just right now. And we are going to fix it before shipping Oilpan for the node hierarchy. And finally, we have a heap visualizer for the Oilpan heap. So each Oilpan object has a header. And in the header, we can retrieve the type information of that object. So by scanning the Oilpan's heap, we can get information of the object types of all objects. So objects in Blink are under our control. So this visualizer can visualize what Blink objects are doing. So for example, it can visualize the number of marked objects, or number of free list entries, or free size, free ratio, and so on. And also, for each object type, it can count the number of generations of the object. The object survived how many generations, and how many objects we have in the program, and so on. And this visualizer is going to be integrated into about tracing by the memory infra work. So this is going to happen in the near future. So what's the next step of Oilpan? So of course, the step one is shipping and stabilization. And the step two is more optimizations. So the step one is shipping. So shipping means drop will be types. So this is going to be challenging because core is huge. It contains node, CSS, SVG, AX objects, frame window, and so on. So I believe that incremental shipping is a key to get things stabilized. So we are trying hard to ship Oilpan for event targets, CSS values, nodes, and so on, as separately as possible, and stabilize that architecture in trunk. And our current plan is to enable the Oilpan flag in trunk at least once by the end of Q2. So I don't think we can make success here at the first try. And I'm pretty sure we have to revert the patch a couple of times. But at least we want to enable the Oilpan flag at least once by the end of this quarter. That's our schedule. So the step two is more optimizations. So there are a lot of room for Oilpan to make it even faster. So one idea is to implement type-specific generational garbage collection. So currently, Oilpan is a very straightforward mark and sweep GC. So all objects are collected in major garbage collections. So the pause time is order number of live objects. So by implementing type-specific generational GC, we can collect most objects in minor GCs. And the pause time of the minor GC is order number of live objects in the young heap. So which means that we can reduce the pause time of most GCs by implementing type-specific generational GC. And another optimization idea is compaction. So in Oilpan, objects are going to be movable. So because all objects are retained by member at the end of an event loop, so we can move objects around and we can just fix up the pointer value. So by doing compaction, Oilpan can improve memory locality and decrease memory fragmentation for long-running applications. So specifically, for example, we can reorder nodes in a DOM traversal order. So by doing this, we can improve memory locality. Or we can compact vector buffers and hash table buffers. Or we can group objects by their types. So this is because objects of the same type are likely to be accessed together. So grouping objects by their types can improve memory locality and improve runtime performance. So this is about Oilpan. So any question until here? Okay. So the second action item is optimize partition alloc. So the lesson we learned from Oilpan is memory locality is very important for runtime performance. So this lesson has a lot of implications. So for example, so it is important to understand Blink workloads. And it is important to optimize allocation schemes. And it is important to reuse memory as much as possible. And it is important to group objects by type because the same type objects are likely to be accessed together. And also, it is important to reduce size of DOM objects. So this is because if the size of DOM objects is small, we can pack more objects in a small address range. So by doing this, we can reduce the number of CPU cache misses. So this is in particular important for nodes and layout objects. So because nodes and layout objects are traversed in a tree order. So if size of node is 10% larger, which means that CPU needs to fetch 10% more data from the memory, so which decreases the performance. So at first, I didn't think size of DOM object is important because Blink is not a main memory consumer. However, I realized that size of DOM object matters for runtime performance related to the memory locality. So anyway, we are planning to optimize partition alloc based on these experiences we learned in Oilpan. So this is another example. So in this code, we are allocating 3 vectors and appending nodes to these 3 vectors. So for this supermicro benchmark, if we use vector on partition alloc, it takes 680 milliseconds. On the other hand, if you use heap vector on Oilpan, it takes only 170 milliseconds. So Oilpan is 4 times faster. So why? So this is because Oilpan cleverly allocates vectors so that vector.append is realized just by expanding the existing underlying buffer in common cases, which means that vector.append doesn't need to reallocate and copying the buffer in most cases. So this is basically based on heuristics, but according to my measurement, the succession rate in real-world applications is more than 96%. And we are planning to apply this same optimization for partition alloc. Any question here? Johan?
Do you see a similar performance speed up on top 25 or the smoothness benchmarks, or is it just micro benchmarks?
So I'm not sure is the answer, but at least we can observe the performance improvement in micro benchmarks. And when we are working on Oilpan, we have observed 5% or 10% regression in speedometer. However, by optimizing these allocation schemes, we can mitigate that regression in speedometer. So it is expected that these optimization will improve performance of speedometer or something like that, but we are not sure.
Okay. And do you know how the the optimizations you described for vector would probably also work with the ref counted ones? Do you know what the performance improvement was if we would apply the same kind of optimizations to the existing code?
So your question is where the performance improvement comes from?
Yes.
Yeah, so actually we haven't yet broken down the performance improvement, so we are not sure.
Okay.
So I saw that std vector was a little bit faster than the Oilpan vector. I was wondering, why is that even faster, and can we make the same optimization?
Yeah. So actually, this is because of the overhead of garbage collection. So in this case, we are allocating heap vector here, and the vector becomes garbage here. So actually, I'm running this loop 10,000 times or something like that. So at some point, the garbage collection runs to collect these three vectors. So the 10 milliseconds is the overhead of doing the garbage collection. Okay, Dominique?
In my experience, our tools are really poorly set up for measuring page faults and cache misses, especially on Android. Any help coming?
Yeah, so actually, if we change the size of node or size of layout object, it changed performance over a lot of benchmarks. So we thought it would be because of the cache miss rate. So I tried to measure that number using some CPU profilers, but I couldn't get reliable numbers. So I don't have a good idea for the 2D.
I've also spent a bit of time on this, and it's really hard. And I noticed there are a few ARM people here, so maybe later on we should all get together and have a talk.
So please tell me a good profiler. Okay. Okay, so the action item 3 is partition alloc everywhere. So this is the current status of the allocators in Blink. So it's very complicated. So we have Oilpan, PartionAlloc, TCMalloc, and system allocator. And Oilpan and PartionAlloc are used in all platforms. So however, TCMalloc is enabled only in Linux and Chrome OS. And other platforms are using system allocators. So the situation is messy, so we want to remove TCMalloc and system allocators and want to unify these allocators into PartionAlloc. So the goal is PartionAlloc everywhere. So we want to remove TCMalloc and system allocators from Blink and unify allocators into the Oilpan for garbage collected objects and PartionAlloc for non-garbage collected objects. So what's the advantage of doing this? So reducing the number of allocators is a key to get all Blink objects under our control. And also, PartionAlloc will improve performance and reduce memory. So when we experimented with replacing TCMalloc with PartionAlloc 1 year ago, there was a 5 to 10% memory saving in a renderer process and a 30% memory saving in a browser process. So in this experiment, we created a dynamic library of PartionAlloc and completely switched allocators in Chromium entirely. So this is the memory saving we observed. So actually, I want to make it actually happen. So this is our goal. So the open question here is, what does everywhere or the PartionAlloc everywhere mean? So in short term, we have a concrete plan to replace everywhere in Blink. And in long term, maybe we want to replace allocators in Chromium with PartionAlloc. However, we are not sure. So regarding the allocators in Blink, Tasak already started the experiment. And we are going to publish a design document in this quarter. So any question until here? Okay.
Are you going to have unique difficulties moving away from system allocators on platforms that are not Linux and Chrome OS? So the question was, you're using TCMalloc on Linux and Chrome OS. Are you going to have unique difficulties moving away from the system allocators on the other platforms?
Yeah, so for example, in Mac, Blink is still using CF string, and that implementation still depends on the system allocator on Mac. So however, Tasak has a plan to remove CF string from Blink. So that is one reason for Mac. And in Windows, I'm not sure, but TCMalloc does not free the allocated address forever in Windows. So TCMalloc does not call virtual free in Windows for some reason. That's why we cannot use TCMalloc, but that problem is already fixed in PartionAlloc. So I don't think it's hard to replace the system allocator with PartionAlloc somehow. So anyway, so there are a bunch of problems around here. So I'm not sure how easy the replacement will be. Thanks. So in question? Okay. So the final one is memory coordinator. So let me describe the problem first. So we have caused a bunch of out of memories like this. So V8GC or Oilpan GC are not properly triggered because V8 or Oilpan are not aware of the amount of memory consumed in their embedders. So in this example, a big string is retained indirectly by the V8 object. But if V8 is not aware of that memory, V8 won't trigger garbage collection. So in that case, we will end up causing out of memory. So in the good old days, the problem was being solved by an accounting API in V8. The accounting API lets each embedder report the amount of memory used in the embedder. So then V8 can understand the amount of memory used in the embedders and properly trigger V8 DCs. So this mechanism was working as long as the lifetime relationship was relatively simple. So however, that is no longer the case in the current Blink. So the relationship is complicated. So for example, this can frequently happen. So V8 object is retaining the DOM object by Oilpan's persistent handle, which retains the DOM object using Oilpan's member, which retains the DOM object using on pointer, which retains the big string using left pointer, and so on. So that string is indirectly retained by the V8 objects and Oilpan objects. However, it's unclear what allocators are charged on what. So it's not clear we should report the memory to V8 or Oilpan or both. So it's not clear. So the problem is the accounting API doesn't make much sense in a world where the object retaining graph is complicated. And we have multiple allocators, V8, Oilpan, PartionAlloc, and so on. So in more general, the problem is each allocator is highly optimized. So for example, V8 and GPU buffer already have memory saving mode. So these allocators are highly optimized. So however, the problem is so each allocator is working without having a global knowledge of the memory usage of other allocators in the renderer processes or other renderer processes or Chrome or OS. So this is the problem. So we are proposing memory coordinator. So the memory coordinator has a global knowledge about the memory usage of all allocators in the renderer process. And the coordinator is expected to send notifications to each allocator so that the allocator can take proper actions. For example, trigger DCs, or so Oilpan or V8 can trigger DCs, and the skier can drop font caches, and the GPU buffer can drop discardable memory, and so on. So the memory pressure listener is the idea to implement the coordinator. So memory pressure listener can send basically two kinds of notifications, medium and critical. So medium means please fall back to a memory saving mode. And critical means we are near OOM. So each allocator is expected to listen the notifications and take proper actions on receiving the notifications. So we are now planning to implement the memory pressure listener for all allocators in Chrome. So this is already working in Chrome OS, but not yet for other platforms, and not yet for V8 and Blink. But we already have design documents for that, and we are planning to implement it for all allocators in Chrome. So okay, so the conclusion. So we are working on the Blink allocator, and the goal is to develop the best memory allocator in Blink that is fast, secure, and space efficient. Fast means 60 FPS DC, small allocation overhead, and good memory locality. And secure means no use after freeze. And space efficient means no memory leaks, no out of memory, and small footprint. So specifically, we are working on shipping Oilpan. So this is the first priority. And optimize PartionAlloc and PartionAlloc everywhere, at least in Blink. And we are also working on memory coordinator in order to avoid causing out of memory. So that's it. So any question? Yes.
Yes. So I just have a question about the memory pressure listener. I was wondering if that's meant to be a general I guess something that can be repurposed to track any type of resource that's held by objects that could be awaiting garbage collection. For example, file handles, GDI handles, GPU resources, just anything that we have a limited number of that we would want to use as a trigger for garbage collection. Is that the intent, or?
Okay, so basically the memory pressure listener is going to observe the memory used in OS and decide which action should be taken in each renderer process. For example, for active types of the Chrome, so for non-active types, we can send notification to say memory saving mode and so on. So basically, the trigger will happen based on the memory used in OS.
Okay, because something we've struggled with a lot in recent years is objects awaiting garbage collection that are holding on to GPU resources, for example, a large GPU buffer, and then where the system is running low on GPU memory, but the V8 heap is not aware of that, or we report the allocated memory, but it's accounted as if it were RAM, and we don't have the same RAM limit as the GPU memory limit is different. So we've been struggling with that, and I was wondering if you had a solution to propose for having, I guess, a more generalized interface for having custom garbage collection triggers.
So you mean you want to trigger V8 garbage collection from GPU buffer?
V8 or Oilpan. Basically, if I have, for example, a limited number of, just to give a generic example, let's say your OS allows you to have, a maximum of 1,000 file handles, and you have these objects that are no longer referenced, that are holding on to file handles, and you need their destructors to be called to make file handles available for another usage. So that's not memory pressure, it's just a different type of resource pressure, but we would like the garbage collection, we'd like to have a garbage collection trigger for that.
Yeah. So actually, I'm not familiar with concrete APIs of the memory pressure listener, but the basic idea is that in that case, each allocator, for example, the GPU buffer, can send some request to the memory pressure listener at the top level. So the memory pressure listener can understand that request and probably send a notification to each allocator to cause this, for example. So
okay.
That's the basic idea. Yes.
So in general, our experience with external GC triggers, and that basically also holds true for an out-of-memory thingy, is that usually the entire system has failed and you're in deep trouble. So adding explicit GC APIs is basically just asking for deep trouble. Instead, what we should do is that the system that actually manages those resources, and like if it's a GPU resource that is directly or indirectly held via a V8 object, then the garbage collector needs to know about these resources and about the kind of constraints we have. So trying to solve these problems by adding explicit hooks that say like, oh, just collect some garbage in the hope of freeing up a resource is almost always the wrong thing. Like there are special cases like, the memory pressure when Android tells you, hey, I might just have triggered a kill for you, so maybe you managed to free up resources before it arrives. Then yes, that is maybe a good trigger for garbage collection. But it's kind of an indication that we failed before to manage resources. But we shouldn't build a system that relies on, just collecting garbage in the hope of freeing up a resource. But instead, we should find a solution to explicitly manage these resources.
So any question? Over there?
Do you have a general timeline for each of those steps? Is like the memory allocator a couple of months away, a memory coordinator a couple of months away, or a couple of years away, or somewhere in between?
Yeah, okay. So regarding shipping oil pan, so our plan is to enable the oil pan flag in trunk at least once by the end of this quarter. So this is the timeline. And regarding optimized partition alloc, no one is working on it yet. And regarding partition alloc everywhere in Blink, Tasak started the experiment, and we are going to publish a design document about our concrete plan by the end of this quarter. And I'm not sure how hard it is, so depending on the platform-specific problems like you mentioned. And regarding the memory allocator, the Chrome OS people are already working, and I'm not sure the current status, but this is actively working. So that's the situation. Yes.
PartionAlloc looks really exciting. Are we thinking about making that a separate project so that it can be incorporated into other things? I mean, if it's better than tcmalloc for us, why wouldn't it be for other projects?
So what is the question?
Would we consider why is PartionAlloc part of Chrome? Why isn't it a separate library so that other open source projects and other potential projects can use it if it's that much better than tcmalloc?
Yeah, so actually, it's hard to say in general that PartionAlloc is better than tcmalloc. So because PartionAlloc is originally designed for Blink, which is mostly single-threaded. So on the other hand, tcmalloc is designed based on the multi-thread architecture. So currently, the threading support in PartionAlloc is weak. So because it is grabbing spin lock when allocating an object. So in order to use PartionAlloc everywhere in Chromium, I think we need to improve that architecture. And another reason is that PartionAlloc is aiming at more security reasons. So it never reuses the freed pages for different size of buckets and so on. So which can end up a lot of which can eat up a lot of virtual address space. However, it doesn't happen in tcmalloc. So this is completely okay in Blink, but I'm not sure how general this assumption is in the Chromium. So we need more investigation. However, we want to do that. So any other question?
This is a question about Oilpan all the way back to the start. So when you started Oilpan, there was this argument that, hey, like we won't have ref counting anymore. We're just going to write these pointers, and so it'll be really fast. And now you're going to do generational stuff, which means you're going to have to like write barriers when you see things going to the old generation or whatever. So I guess I'm just curious, like, how's that going to work? Is Member going to have to look at some globals about address ranges and stuff? Like, how will it work?
Basically, so from the programmer perspective, there is no change. So we can just add one macro in each class. For example, animatable value should be treated as generation or something like that. One macro is enough. So no developer burden. Yeah.
So you're just going to apply that macro to things that you find die very quickly. Yes. Something. Okay. Cool.
So any other questions? Okay, so thank you very much.